just out. Feel free, doesn't matter. Feel free to move around. Welcome to this a little bit unusual day for our seminars, but we'd like to take the opportunity of having our visitor today, Schäpers, who is visiting us from Jülich Research Center and Aachen University. Thomas did his studies in physics at Aachen University. He obtained his degree in 1989, and then he did his PhD in Jülich about the ballistic electron transport in 2D systems. And after that, he went for postdoc in the MIT. He spent 2 years, 1 year, sorry, working on photon-assisted time. And he has, as I mentioned, a position in Aachen University and in the Jülich Research Center. He would, I think, tell us about his research interest in general, and he's well known for his work in spintronics, properties of semiconductor systems, in which Spinorbit interaction is very relevant. I should also like to mention that we had the opportunity to participate in a joint application to the European Union that we want to try again soon. And with that, I think thank you very much.
Yeah, thank you very much, Jonas, for this nice introduction and this very kind invitation. It's a little bit strange to be here for working on Mallorca Island. I think every German was here at least once for vacation. And when I was in the airplane, I think I was the only working guy reading papers. But okay, it's a pleasure to be here, and I enjoy it very much. And I will give a presentation today about our activities on semiconductor nanowires. So we do a lot of things with these semiconductor nanowires, and I will try to show you at least part of this we're doing in Jülich on this subject. Before I start, I would like to show you where we're working and living, because I think Jülich is not that much known here. So it's opposite. Everybody knows in Germany where Mallorca Island is, but where Jülich is, I'm not sure about. So if you have Germany here, it's North Rhine-Westphalia, so we're here on the west side. Jülich is in that area here. It's a small town, about 30,000 people, and Aachen is here. So Aachen is famous for its cathedral. It's Aachener Dome, which is from Charles the Great. Actually, this is the Spanish name of Aachen, maybe you know this better for that. And Aachen University is one of the biggest technical universities in Germany. And Jülich is, they also have an old fortress. That was, I think, the reason why Jülich was destroyed during the Second World War, because somebody thought these old structures are relevant. And so Jülich is newly built, more or less, and at the side of Jülich, we have the research center, which has where about 4,500 people are working on different research subjects. So the origin of the Jülich Research Center was nuclear research. So there were some nuclear reactors here, but now we are, I would say, a kind of department store of science. So we do almost in all fields we're contributing. So in medicine, in material science, in information technology, and so on. We have a strong collaboration now. It's called JARA, Jülich Aachen Research Alliance, and our branch is called JARA FIT. It's Fundamentals of Future Information Technologies. So there, the Aachen University and Jülich Research Center are working closely together. We have joint research projects and so on, joint lectures. So the distance is not that big, so it's like 30 kilometers, so quite close. So I would like to tell you something about our nanowire research, and here you see some example how these nanowires look like. We have, for instance, indium arsenide nanowires. I will talk about more details later, but you can use these nanowires, so the diameters are about 100 nanometers. You can use these nanowires for mainstream technology, so transistor applications. You can use that for spin transistors, if you like, and we'll talk about this. And also you can use that for single electron tunneling. So that's a structure where you use additional gates. And we are interested in phase coherent transport, so what do the electron waves do in these nanowires, and also we are interested in the spin transport in nanowires. So first I will give a general introduction about the nanowires itself, so how does they look like, how do we make these nanowires, and then I will switch over to phase coherent transport, so the wave properties of electrons in these nanowires, and then move over to flux periodic oscillations we see in special kind of nanowires, in these tube-like nanowires, and at the end I will discuss how the spin comes into play if we have these nanowire structures. Now here is first introduction how we grow these nanowires, so how is the technology to grow semiconductor nanowires. It's not like in the garden, but we have also a substrate, so a ground where the nanowires are grown. We do it in that way that we have the semiconductor substrate, so this can be gallium arsenide or indium arsenide. This is covered by a thin layer of anorganic resist, HSQ it's called, and by electron beam lithography we prepare some holes here, and in these holes the nanowires grow by metallogenic vapor phase epitaxy, MOVPE. So that's a special technique. By that technique you can determine where the nanowires grow, so it's in contrast to most other methods. Here we can really determine where the wires are growing, and we know exactly the position. At the end it looks like this, so you see a very regular field of nanowires. The growth depends on the distance and so on, but in general the diameter is around 100 nanometers depending on the growth parameters and so on. And the length can be up to 5 micrometers. So that's the dimensions we have. If you look a little bit closer, that's an interesting issue we're studying on these nanowires. If you look from far away, you think, oh, these nanowires look perfect. But if you look closer, and if you look at transmission electron microscopy, you see that the crystal structure isn't that perfect. That's something you often have to deal with if you have nanowires. The crystal structure is kind of messed up. And the reason is that in contrast to layer systems where it's well defined which crystal structure you should grow, if you have a nanowire in just a small area, it's not that clear what is the best crystal configuration. So there's a competition between Wurtzite and zinc blende, and in fact both happens here in the nanowire. So the nanowire decides by accident or by energy reasons what is growing here in this area, like Wurtzite, zinc blende, and so on. So there's a statistical switching between both crystal configuration. And of course, one has to take this into consideration. So this might be a source of scattering, because we have different band gaps in both crystal configuration, and so the potential profile isn't that smooth. Yeah, how to get densely packed nanowires. That was a picture I took 1 year ago when we were on vacation in California. And at Mammoth Lakes you find these pillars here, and I immediately saw they look really like nanowires. You see these pillars here, these are I think volcanic origin, and if you look from the top you see this hexagonal shape like we have in a nanowire. And if you look now how the nanowires are grown, it looks very similar. Here you see a field of nanowires, so if you look closer, you see that you have really densely packed nanowires. This is a special method we're using. This is nano imprint, where you can use a print method to make in one instant a whole field of holes in the substrate, and then you can grow the nanowires. So this is a very effective method to fabricate nanowires very quickly, let's say in one run with lithography. Yeah, what is funny, if you touch the nanowires, you can play like nanowire Mikado, and so you have to be careful. That's actually the way we are detaching the nanowires. They easily break at the bottom, and you can take the nanowires and put them on a fresh substrate. So that's the method we're actually using here. We have other methods to fabricate the nanowires. It's molecular beam epitaxy, so it's not with a gas source, but in a vacuum. Here the method is slightly different. We're using a plain anorganic layer of coverage of a silicon wafer. And here you see the nanowires grown. The reason why they grow here is that you have some pinholes in this mask layer, and in these pinholes the nanowires grow. So this is an alternative way to grow the nanowires. The way of growing is slightly different. So here you mainly have zinc blended crystal configuration, but you have these twinning. So you're switching the zinc blend, the ordering of the zinc blender order from ABC to CDA, so the other way around. And then you have these twinning planes here in between. Yeah, so that's something different compared to the method I showed before. The last one I want to show you is a different material. It's indium nitride. This is also grown by MBE, molecular beam epitaxy. So these are a typical example of indium nitride nanowires, and indium nitride usually has bullseye structures. So this is compared to indium arsenide, a different material. You have different band structure, and you will see later why this is maybe interesting for nanowires. So what is the advantage of using indium arsenide or indium nitride for semiconductor nanowires? The reason is that in these semiconductors, the band structure is in that way that we have a small band gap here. Yeah, so here you have the valence band, you have the conduction band here, you have a small band gap. For indium nitride, it's 0.7 around, for indium arsenide, 0.4. And interesting thing is that the conduction band goes deeply down almost to the valence band here. But you have a small density of states here. Yeah? And this is the reason why you have a certain surface configuration at the end. Yeah? And that's shown here. So what determines the surface density of states is the average density of states you have here in your bulk semiconductor. And you see here you have a lot of states here, you have a lot of states here, but almost nothing here. And this determines how the surface states are distributed. And the fact is that because there's almost nothing here, the average point is here, and this is what determines the kind of Fermi level of the surface states here. So below that you have donor-like states, which are occupied usually if they are detached, and here you have acceptor-like states, and the Fermi level is around here. That's a charge neutrality level here. And so if you, by a Gedanken experiment, if you attach both, then the electrons are getting transferred into the conduction band here because it's energetically favorable. And what happens is that you have a surface accumulation layer. So you accumulate electrons here, you're missing electrons here, you have a positive charge here, and electrons are transferred into the bulk semiconductor at the surface here, and you have a two-dimensional electron gas right at the surface. And this is, of course, a big advantage if you compare now this kind of semiconductors with gallium arsenide. If you have indium arsenide, indium nitride, or indium antimonide, then you have the surface accumulation layer here, so you can be sure that you always have electrons in your nanowire. Now that's a big issue if you want to do transport experiments. You would like to have some electrons in your nanowire. If you compare that with gallium arsenide, for instance, you have the opposite because you have a different band structure. There aren't electrons transferred into the bulk semiconductor, but the electrons are transferred into the surface state, and in that case you have a depletion layer. Yeah? And you can imagine if you have this kind of semiconductor, then if the nanowire is smaller and smaller, you're losing all the electrons here because you have a complete depletion of the nanowire here. Yeah? So in this sense, it's the best choice to have these narrow bandgap semiconductors so that you can rely on the surface, on the accumulation layer here, that you have a natural two-dimensional electron gas. Yeah? If this electron gas is really as nice as I showed here, that's still something to discuss and still something to study. We do experiments on this, and we're still not sure how in detail this looks like. Yeah. So how do we fabricate our nanowires for transport? What we need is we have to put on some contacts to the nanowires. And the first thing we're doing is that we have, not really a lawnmower. It looks like a lawn, these nanowires, but we detach the nanowires from the original substrate, and then we put them on a fresh substrate, which is with alignment markers here. So you have on the fresh substrate, on the new substrate, you have alignment markers. You puts the nanowires here randomly on the surface, and the next task is to find these nanowires to get contacts on them. So you do it like in that way that you do electron beam microscopy. You take a picture of the sample, and then you see where the alignment markers are, you see where the nanowires are. This helps you to design, by electron beam lithography, to design the contacts so that later on the structure looks like this. So we have the nanowire here, we have the contacts here, and we have gate structures. So for each nanowires you have to do this individually. Yeah? So that's a big work. Yeah? All the students are complaining to do that. For each nanowire you have to design the contacts individually. So you need a lot of time and a lot of music in between so that you can stand this work here. But that's a simple Stone Age method, but it works quite nicely for research experiments. Yeah. So at the end, the structures look like this. Yeah? If you have a nanowire here, we have different ohmic contacts here, or you can have also gate fingers where some dielectric is in between to isolate the gate from the nanowire. So that's the technology we are using. And you can see here, these are typical examples for transistor structures. So this is the source drain voltage here, the drain current. But here we change the gate voltage, so you see that you have a nice transistor action here. So that's a gate here which is controlling the conductance of the nanowire here. And we can do the same for shorter gates here. So you have short channel effects you see here. So in principle you can use these nanowires for transistors, and that's actually one of the way electric engineers are thinking of, that one can use these one-dimensional structures for making more efficient transistors, because the control of the conductance is going from all sides here, which is more efficient than if you have a layer system where you control just from the top. So this is a very hot subject for ordinary transistors, let's say. What is one specialty in our institute is that we can even dope the nanowires, that we can increase the conductance of the nanowires by putting some silicon into the indium arsenide here. And you can see here, we call that doping factor 1 because we don't know exactly how to quantify how efficient the doping is. We can just say how much we put into the gas here. So this is doping factor 1. We have a large resistance here, and here we have doping factor 250, so 250 times the doping we have here. And you see that we can decrease the resistance of the nanowires by 2 orders of magnitude here. Yeah? What is shown here is the length, so the longer the nanowire is, of course, the larger the resistance gets. But what you can see from that is that if you dope the nanowires, doping is working. What is not trivial. Yeah? You have to prove that at the beginning that you are able to increase conductance by doping, which is for these nanowires not clear from the beginning. What you can see here, this is the increased doping. You see that the conductivity is increasing, so you have a large increase of conductivity, and this gives you an additional degree of freedom. So you can, if you would like to make transistor structures, you can design the conductance of your channel to optimize the transport in the nanowire. And of course, you can also look, if you do field effect transistor measurements, you can look on the mobility. You see that if you increase the doping, you increase the mobility. And what we think of is that if you increase the doping, what happens to the electrons? If you look here, this is the electron concentration, this is the border of the nanowire, that's the axis of the nanowire. If you have almost no doping, you have an accumulation layer right at the surface, as I explained before. So you have a lot of surface and interface scattering, because the electrons are directly seeing the interface here. But if you have a large doping, if you do a calculation with the Schrödinger-Poisson solver, you see that the electrons are flooding the complete nanowire, and then you have less scattering because a lot of electrons are in the middle of the nanowire, and that's why the mobility increases. That's at least what we think of this here. What I said is that also you have different band structures, so you different crystal orientation. You have zinc blende and woodside structures here. And if you look at the band gap, you see that the woodside structure has a slightly larger band gap. So if you look along the nanowires, what you expect is that you have some steps in the potential which somehow influences the transport here. That's what you see here as well. If you increase the doping, you increase the Fermi level, and then it's getting easier for the electrons to get transported through the nanowires because the barrier they have to overcome here is getting smaller. Yeah? And that's what you see here. If you have a low doping, you have a larger thermal excitation here. Yeah? And if you increase the doping, this high doping level, it's almost metallic because then you have so many electrons that the Fermi level is presumably above all this, and then you have a better transport. So this is something you have to be very careful if you look on these nanowires. Often they're not as ideal as you think at the beginning, that you have different crystal structures and that you have to take care of this. Also what can happen is that you can have defects in the nanowire. So if you measure the nanowires, if you measure it carefully at low temperatures, you see these Coulomb diamonds here, so you have single electron tunneling. Yeah, so what we think is that if you get the transport here, that you have defects in the nanowires which form some barriers, and then if you measure the transport, you see these characteristic Coulomb diamonds, which is an indication that you form some quantum dots here. And actually you can do that in more detail if you do a so-called scanning gate technique. You can, by scanning the gate here, it's like this with a tip of an STM or an AFM tip, a conductive AFM tip, you can put a voltage here, and by scanning this tip here along the nanowire, you can change the potential in the surrounding of the nanowires, and this tells you something about the transport here. So if you measure the resistance here, the resistance is influenced by the potential of the tip here. And if you do this systematically, you can even identify where the quantum dot is. Yeah, so here you can, by having these equipotential lines here in the transport. So this is the grayscale here is the resistance of the nanowire. Yeah? And so you see if you go in a circle around the quantum dot here, you get the same conductance here. Yeah, that tells you that the quantum dot itself is in the middle of the circle. Yeah, so that's a way to analyze in more detail and more locally what's happening in this nanowire. So this was all some introduction how the nanowire works in general, how you can control the conductance of the nanowire, and how you can manipulate the nanowire. Now I would like to go to more basic phenomena, and the first thing is I would like to talk a little bit about electron interference. You probably all know the Arnold-Bohm effect, where you have a structure like this here, where you have a ring-like structure, so you have a magnetic field perpendicular to the ring, and as a function of a magnetic field, you get some regular oscillations which are flux periodic. That's what you observe. And if you look in experiments, that's what we did some years ago, 10 years ago, on these gallium arsenide Arnold-Bohm rings, you see very regular oscillations here which can be controlled by a gate. This phenomena, in principle, can also be seen in nanowires. If you think of a nanowire having some scattering centers here, then you also have some phase coherent transport, and the question is, what is the phase coherence length here? What is the maximum length where you can keep the phase coherence in the nanowires? And that's what we like to study, and we do that by studying the universal conductance fluctuations. This is a very interesting method to get information on the phase coherence, because you have a small structure, the nanowire is a small structure, and you have a finite number of scattering centers here. So in the transport you see a fingerprint, so each nanowires behave different, and what you see in the transport is you see some conductance fluctuations. And how does it work? It's the same as the Arnold-Bohm effect in principle. So what you have in the Arnold-Bohm effect is that you have a closed loop, and you can have this as well if you have scattering centers. You have
Sorry, in this case the magnetic field is transverse?
Yeah, this is transverse here. Yeah, but in other experiments the magnetic field is along the wire. Yeah? For this experiment the magnetic field is perpendicular to the wire. So some interesting thing we should study in the future in more detail. Yeah. So here the magnetic field is in that direction, and here you have some one area where you have a closed loop, and then you have this Arnold-Bohm effect, and the period is given by the area here. But of course you have different areas as well. Now this is slightly larger, so you have a smaller period. You have other areas, and if you look at the end, you see a very messy conductance here, so fluctuating conductance with the magnetic field. And these are the universal conductance fluctuations, which are universal, because if you look at the root mean square here, it's just E squared over H in the order. Yeah? So you always end up with this conductance fluctuation if you measure this here. But this is only an ideal case. If you have phase breaking in between here somewhere, then this factor is reduced, and this reduction is given or determined by the phase coherence length. So if you do that the other way around, you can get information. If you look at RMS here, you can get information about the phase coherence length and study this by looking at the universal conductance fluctuations. So that's what we did here. So we have a set of nanowires with different contact separation. So here we have a short contact separation. It's getting longer and longer. What you observe here is that we first of all see these conductance fluctuations. They are reproducible. So if you repeat the measurement here, you see that the fluctuations the pattern is the same. Here the amplitude is decreasing if you increase the temperature, but the pattern is the same. What you see here, if the nanowire is longer, you have more fluctuations here. The temperature dependence is also different. You can plot this in a two-dimensional scheme here. So here is the temperature, this is the magnetic field, the color is the amplitude. You see that for the short nanowire, the fluctuations remain to much larger temperatures here, while for longer nanowires is cut off very quickly. That's what we look at. We study now how do the fluctuations change if we change the length of the wire, and can we get some information about the phase coherence length here. And that's the result. If you look in detail, what is plotted here is the fluctuation amplitude here, the root mean square as a function of temperature. If you have a long wire, then the phase coherence length at large temperature is short, so then we have a lot of inelastic scattering in between. We have no ideal case, so everything is determined by the phase coherence length here. And if we increase the temperature, the phase coherence length increases, and then RMS is increasing as well. You can observe this, and also if you have a shorter wire, it's the same. Here we have phase coherence length shorter than the nanowire, and if we increase the temperature, it's getting longer, but it's still in the order of the nanowire. But if you have now a very short one, then you see that at a certain temperature, then the phase coherence length gets longer than the nanowire, and then you see a plateau here in RMS. Then you reach the point where the phase coherence length is longer than the nanowire, and then if you decrease the temperature further, then you don't gain anything. Then you still remain with this constant root mean square here. It's the same for even shorter nanowires. So at the end, what you observe is if the nanowire is shorter, then at a certain point you get a plateau here, and the plateau is that the phase coherence length is now longer than the nanowire itself. And then you can plot this as a function of temperature for different wires here, and you see that the phase coherence length at first follows this line here, and then it's cut off simply by the wire length. So that tells you that if the contacts are short enough, and if the temperature is small enough, then you have a complete phase coherent piece of wire there. And so if the nanowire is longer, you have to decrease the temperature further. But you see here, if you tell you some numbers, if you have like less than 1 Kelvin here, you have phase coherent lengths in the order of several hundred nanometers here, so 400 nanometers in that case. So that's what you have in these nanowires. So that's a typical length scale where you have phase coherence phenomena in the nanowire. So let's move over to more fancy structures. What we worked on recently were core shell nanowires, where we have the gallium arsenide, which is non-conductive. It's a high bandgap semiconductor. I told you before, you don't expect any electrons here in the nanowire, but we wrap around some indium arsenide here. Now that's a structure where we have now a tube-like conductor, where we have something which is non-conductive here and a conductive shell. So it's a core shell nanowire. And the measurement configuration is like this. So now the magnetic field is along the nanowire. So that's opposite to what I showed before when the magnetic field was like this here. But now the magnetic field is along the axis of the nanowire. And what we're studying is what's happening to the transport in these nanowires if we apply a magnetic field. And the important thing is the magnetic flux we encircle here. Yeah? So we have an electron system, and we apply a magnetic field. And what you expect, similar to the Aharonov-Bohm effect, is that we have some flux effect here on the electronic state. Now that's what we're studying, and that's what the transport. That's the transport experiment we are doing. And here you see the result. This is a magnetic field here. This is a conductance. This is more or less raw data, so this conductance we measure the resistance, but this simply calculated the conductance with also some universal conductance fluctuation here. But if you see it immediately that there are some very regular oscillations here on the conductance. If you do a Fourier transform, you see all the time you can do a backgate measurement to change the electron concentration. But no matter what gate voltage you apply, you always get a peak at a certain position. And if you calculate and compare that to the magnetic flux, then you see that each time you add another flux quantum to that cross section of the nanowire, then you have one period in that conductance or oscillation here. Yeah? So that's what we observe. This was for a short piece of nanowire, so the contact separation was 100 nanometer. This was for a longer piece. We also see that the diameter is slightly different because of some growth reasons, but it's still one single flux quantum period. You see the conductance here of the nanowire. This is more colorful, but basically the same. What you see here is the conductance color-coded here. This is the gate voltage, this is the magnetic field. So what you see here, this pattern here tells you that we have all the time the same period, but we have some phase changes. Yeah, this is because depending on the gate voltage, you change the interference conditions, and because we have a two-terminal measurement, we have either a maximum here at zero magnetic field or a minimum. Yeah, because we have a two-terminal conductance here because of Onsager relation. This has to be symmetric with magnetic field. Yeah? This is all true for 70 nanometers, 100 nanometers, 370 nanometer lengths of the nanowire segment. And if you do the Fourier transform, you see that for each gate voltage, you basically have the peaks at one fixed position, which is compatible to one flux quantum here in the cross-section of the nanowire. So what is the origin of these flux periodic oscillations? You can first think of that it's kind of Aharonov-Bohm effect, where you have trajectories of electrons going around this nanowire here. But the nanowire is pretty small. Now we're talking about 100 nanometers here. So in 20 nanometers 20 nanometer thickness of the indium arsenide shell here. So it's a pretty small object. So we rather think that this is not really due to some electron trajectories, but we're thinking of having some angular momentum states here which are responsible for this transport phenomenon. So that's why we calculated by a Schrödinger-Poisson solver, we calculated the electronic states here. So what you see here, this is gallium arsenide, this is a conduction band profile. We have a quantum well here where the electrons are located inside of indium arsenide, and this is the surface here of the nanowire. Yeah? So you have a quantum well, but you have to think of having a circular state here. Yeah? So this is just a cross section along, just a cut along this direction. So what you get is you have these confined states, and then you have this ladder of states because of the angular momentum. Yeah? So the angular momentum is going from 0 to 9 or 10 or whatever. Yeah, the Fermi level is here, and fortunately we have the Fermi level, at least in our calculation, the Fermi level is within the first level, so the first excited states, the green lines here, is above the Fermi level. Yeah? What determines the energy spectrum here is, on the one hand side, because we have the circular motion of electrons, we have the angular momentum. It's the angular momentum state here. And if you apply a magnetic field, you also have to include the vector potential, which ends up in this term here, which mainly puts in the magnetic flux normalized to the flux quantum. You know, that's what determines the potential. And we would like to look at the magnetic properties. So we have to look how do these states we have here change with magnetic field. Yeah? And because we have this quadratic flux dependency, we get this energy spectrum here. So these are the levels we have here, yeah, on this here. And if we now apply magnetic field, because of this flux we put into that wire here, yeah, we change the energy levels with B squared, basically. Yeah? And that's what you get. So you get this mesh of states here. And the question is now how we get the regular oscillations in the conductance. And the explanation for that is that you have to look how many one-dimensional states you have. When the energy values are can be written like this. You have these quantized states because of the angular momentum, because of the magnetic field, the flux. That's this here, the flux is here, the angular momentum is here. This gives you this state here, which is flux periodic. So if you look here, the period is one single flux quantum. But of course, you also have the transport along the nanowires, which is this here. Yeah, that's just the transport along the nanowire. So you have one-dimensional states. You have something like in a split-gauge quantum point contact. So ideally, the conductance should be just the number of states here multiplied with the general conductance unit of 2e squared over h, like in a split-gauge quantum point. And if you look now, how many states do we have which count here? For a certain magnetic field, we have here, if you count them, we have like 12 states here below the Fermi level. But if you increase the magnetic field, you end up with one more state here. Here you have 13, and this is going periodically because this structure is periodically. You're switching from one number of states occupied to a slightly higher number by one. Yeah? And so if you look at the conductance, you see that ideally this conductance should be switched by one quantum here back and forth in periodic with one flux quantum. So that's the idea how you can explain the conductance here. Of course, we don't see these steps here. We see some grounding of the conductance, but if you do a more elaborate calculation, as Tserkovniak and Halperin did, they exactly calculated this kind of system where you have a tubular system with this angular momentum. You also see that the conductance here is more or less periodic with the magnetic flux quantum. They included scattering, they included spin-orbit coupling, they included Zeeman splitting and so on. But at the end of the day, you still get these periodic conductance oscillations. So that's what you get if you still look on the charge properties, so the wave properties of the electrons. For the rest of the time, I would like to discuss a little bit spin effects, spin-orbit coupling in nanowires. And to introduce this, I show you the picture you all probably know. It's the famous data-dust transistor, which was realized, it took more than 10 years, or even 20 years maybe, but now it's realized. That's the starting point. Yeah? A spin transistor is proposed by Data and Dust, looks like this. You have some ferromagnetic electrodes, so that's something you need to realize. And then you have a two-dimensional electron gas where you have some electron which is precessing while it's flowing from the left contact to the right contact. And this is because of spin-orbit coupling, mainly Rashba spin-orbit coupling. In this case, you see that it doesn't fit here, so the electrons have the opposite spin direction as the ferromagnetic contact, so it's a red light for the electrons here. And so if you switch on the gate, you can change the spin-orbit coupling, and in this case, the precision is faster, and then you have green light for the electron, so the electron can pass, you have a lower resistance. That's the main switching mechanism for the data-dust spin transistor. Data-dust, they realized almost directly in their original paper that it might be better to have one-dimensional structures. Because then you don't have these different angles of injection of electrons and so on, so you get a higher signal swing if you have a one-dimensional structure. And that's the reason why we look on one-dimensional structure, in our case, on nanowires. Yeah, and so if you look on a typical nanowires, you have indium arsenide nanowires, and I told you that you have this surface accumulation layer, so you have a triangular potential well here. And that's what you need for the Rashba effect. You need some asymmetry in the potential. You need some electric field here, and if the electron is moving in that electric field, it sees effectively some magnetic field, and then it matters which spin direction you have, so which energy you have. Either you have spin up or spin down. Yeah? And so this gives you, at the end, this gives you the spin precession, and that's the basis of the data-dust spin transistor. The main thing is that, I don't know, there's no animation here, but if the electron is moving, while it's moving, it's producing a particular magnetic field here, some internal magnetic field, and if the spin is oriented like this initially, then the spin sees that internal magnetic field and it is precessing around this. Yeah, this is the precession you have in a data-dust spin transistor. And the magnetic field is made by this electric field if the electrons are moving in that field. And then you get this spin splitting, which is determined by the Rashba coupling constant. You can do some calculation. You can calculate in a similar manner as I showed before for the Korshner nanowires. This is the potential here, the triangular potential because of the surface accumulation. You have all these states here. You can calculate the average electric field, and then you can assess the Rashba parameter. Yeah? To be honest, I don't feel that well about this assessment here of the spin-orbit coupling lengths because, as some experts know here, you have to look at the interface here as well. Yeah, how the electron wave is penetrating here into that barrier or whatever this is, into the vacuum state. And for that system, you really have a hard time to know what's going on there. Yeah, so you can do some assessment here, but I would say one can do better if one would know better how the interface looks in detail. Yeah. So how can we measure in these nanowires the spin precession? Yeah, that's what we would like to know. We would like to know how is the spin precessing in these nanowire structures, and we're using weak anti-localization for that. Weak anti-localization is an experimental technique where you can get information about the strength of spin-orbit coupling. So what is that? Weak localization, you probably know, is something that if you have some diffusive systems, the electrons come here, they can either go that way or they can go that way, the time reverse path, and since they meet at the point here as well, back after the surrounding, then you have constructive interference. That means that you have a higher probability for backscattering, and this increases your resistance at zero magnetic field. Yeah, so if you look at the conductance goes down at zero magnetic field because you not only have this here, but you also have other sizes of these loops because you have a random system with random distribution of these scattering centers here. But in all cases at zero magnetic field, you have always constructive interference. And you, by applying magnetic field, you change the phase here, and then you destroy the constructive interference, and that's why the conductance goes up here. So that's the usual weak localization experiment you can do. But if you now include spin and have some spin precession along this way, then the dip here, the conductance, switches to a peak in the conductance, and you have a net destructive interference. You have to include the spin interference here for that mechanism, and then you have a conductance increase. And this conductance increase can be used to get information about the strength of spin-orbit coupling. Yeah, so that's a very convenient way to get information, first of all, about the existence of spin-orbit coupling, but you can also try to get some numbers for the spin-orbit coupling. We measured this by using this kind of structures here. For instance, we have a nanowire here, a source and drain contacts, a gate to change the electron concentration, and so that's the structure. At the end, you need to get information about the weak anti-localization. The reason is that you have some bad thing you have to consider as well. As I showed before, because you have such a small structure, you have conductance, universal conductance fluctuation. And this effect is quite strong and masks all this localization effect. Yeah? And so what you have to do is you have to not only measure the conductance as a function of magnetic field, you get all these fluctuations, but you have to change the gate voltage as well in order to do some averaging at the end to get then some information about the spin-orbit coupling. And this is shown here just as an example. If you look from the top now, this is the pattern of the conductance, so it's fluctuating this zero magnetic field, and what you're doing is you take an iron and just averaging everything, and then you see you get a smooth curve for as a function of magnetic field, and then you see a peak here in the conductance. Yeah, this conductance here you can look in more detail. We have nicer measurements here, but here you can get information about spin-orbit coupling and looking at this peak here, which is due to weak anti-localization. Yeah, this is a typical curve. This was for indium nitride, where you have this weak anti-localization peak here, and from looking at some models for one-dimensional structures here, for instance from Schäpers, you can get information about the spin-orbit coupling lengths in indium nitride. It's about 63 or 60 nanometers, so quite short, quite strong spin-orbit coupling. The reason in that material why that's so strong is because we have such a strong strong potential, so we have a very sharp quantum well here. I can do this. Sorry,
when conductance is negative?
Here, this is because was normalized to zero field. Yeah? So it's not. Here we subtracted the zero field value. Some technical thing. What we're currently doing is what we're working on is that we're looking at indium arsenide nanowires, and we ask ourselves how strong is in indium arsenide the weak anti-localization if you have different doping. Yeah? For instance, if you have no doping, you have a surface electron gas, so you would expect a strong potential gradient here, while we have a largely doped nanowire, then we can maybe expect a smaller spin-orbit coupling. Now that's our current work here. So these are measurements from the last week. So this is a doped nanowire, an undoped nanowire, and you see some differences here in the weak anti-localization. Just to show you how far we are, but we still have to analyze this, but we definitely see that for the doped nanowires we get a sharper peak compared to the undoped nanowires. That's something we try to figure out what's going on in these nanowires if we change the potential profile by doping here. Okay, so we come back to the spin transistor. This is some theoretical work I did together with Andreas Springer also from Jülich Research Center. The question here is, what does the spin do if the electrons move through such kind of nanowire? Because it's not trivial. If you have a two-dimensional electron gas, you can think of you inject the electrons and then they're precessing. Yeah? But it's not that clear if you have these nanowires like this. Do the electrons precess in a circular system as we defined here? Yeah? And so we try to analyze what's going on in these nanowires if we include spin-orbit coupling. So the system is like this. We have a nanowire here, indium arsenide nanowire, with a surface electron gas. We have some internal electric field, which makes you some spin-orbit field here. And we apply an external magnetic field along the wire axis here. Yeah? And you do the same as you did before for a two-dimensional electron gas. You have your spin-orbit coupling term, which is the momentum here, which is the electric field, and that's the spin here. So the faster the electrons are, the stronger is the spin-orbit coupling. And this is the factor you get from the material itself. But for this system, you have to do everything in cylindrical coordinates. So then the spin-orbit Hamiltonian looks like this here, which shows you that you have some k linear term, which couples different angular momentums here because it's off-diagonal. And we have here some Zeeman term, which is because of the ring current in the nanowires. And this is the ansatz for the wave functions here. What you have to quantize everything to the total angular momentum. So the wave functions has to look like this, that you have to increase the angular momentum by 1 because you decrease the spin on the other side to get the same angular momentum. For the spectrum, it has some consequences. I showed you the spectrum before, like it looks like this here. We had some fourfold degeneracy at this point here because we have different circulations of the current this way, and you have spin up and down, it's in total 4. But if we have spin-orbit coupling, we have, because of the angular momentum, we have this circular current and we have the opposite circular current. And this, of course, have an effect on you produce a magnetic field which couples to the spin here. Yeah? And this is the spin-orbit coupling which lifts this degeneracy, and then you have to quantize everything into the total angular momentum. Yeah? So then it counts which spin direction you have in reference to the current here. One can calculate the wave function for this system, and what one sees is that for the different components, you see that if you go around the nanowire, the spin density is tilted along the nanowire. So it's tilted like this here. Yeah? So in total, you have some component in this direction, but if you add up everything along the nanowire, then you see that at the end, you only have some spin direction, some net spin direction along the nanowire, so in this direction, but we don't have anything if we average in this direction here, we don't have any component left in that direction. Although we have locally we have some spin here in this direction, but this is compensated by the opposite on the other side. So on that contact we don't see anything. Yeah. So that's of course a problem, because if you want to have a spin transistor, what you would like to have is this is your nanowire, you would like to have the spin in this direction, and then maybe have a precessing spin, but you don't have this state by just a simple state here. Yeah? And so the question is there a way around by this? And what we found is that you can get these states in the spin which is perpendicular to the axis of the nanowire by having a superposition of states. That's what we looked on here. So if we have, this is the k vector here, this is the energy spectrum as a function of k along the wire. What you see here, these are the states. This is a total angular momentum here. So this is 1/2, 3/2, and so on and so forth. They are coming from L equal to 1, L equal to 2, and 3, and so on. And what you can do now is you can combine two of these states. Yeah? And if you combine these states here, then at the end you get some state, some net state where the spin is oriented. If this is a nanowire here, the spin is now perpendicular to the axis of the nanowire, and if it moves, it precesses. Yeah? So that's good, but the bad thing is that you have exactly the opposite precession also, always, because of symmetry. Yeah? So at the end, if you have one spin in that direction, it can move that way and can move the opposite, and so at the end it's compensated. Yeah? And that's what you get then you get just back and forth of the spin because you have these opposite turning spins here. Yeah? That's what you find if you have zero magnetic field. Yeah, you can walk around by that by applying magnetic field. Yeah? If you apply magnetic field and have all these states, you have in addition, you have a Zeeman splitting, and this Zeeman splitting changes everything slightly, so the states we had were exactly the same, this and the opposite direction are now slightly different, and because they are slightly different, you have one turn which has a slightly larger period than the other way around, and then if you combine those, then you get a spin precession. Yeah? So what you have to do here is, first of all, you have to do a superposition of states, and then you have to apply a magnetic field to make it more asymmetric, and then you get a net spin precession here. So that's, you see that in these nanowires, what you can learn from this is that in these nanowires, the spin transport, because of the different symmetry, is quite intrigued, and you have to start rethinking what's happening in these circular systems if you think of spin precession. So if I have 1 minute, I just show one small experiment, maybe just quickly. What we're working on is that we try to inject electron spins into a nanowire, and for that we put ferromagnetic contacts here on the nanowire. So this is a Semiconductor Nanowires, and these are cobalt ferromagnetic contacts here. And the idea is to drive a current through this electrode here, inject spins, and which can be detected by the second electrode here. That's a usual non-local method of detecting spin injection into the semiconductor nanowire. The problem you have here is the nanowires are quite big, and if you have just very thin cobalt electrodes, you see that they're interrupted here. It's simply because of preparation reasons. And for that, we developed some special technique to cover first the nanowire slightly so that the nanowire is kind of swimming into this dielectric here. Yeah? Like a trunk of tree which is swimming in the ocean, so you see just the surface of this trunk. And by that, by covering part of the nanowire, then we can have a smooth coverage here of the nanowire, and then we get some nice contact to a ferromagnetic electrode. Yeah? And at the end, what one can measure, what you actually do is you drive a current here and apply a magnetic field. And if you first have the magnetic field so that both electrons in the same direction, then you have this signal here. And then if you change the magnetic field so that this electron switches, then you see a switching here in the voltage you measure here. Yeah? And this indicates that you have injected electrons from here into the nanowires which are detected by the second contact here. Then if you apply the magnetic field a little bit further, then both electrons are then in the same direction but opposite to the initial case. Then you switch back to the same voltage as before, because then for the transport it doesn't matter. It's just what you measure is if they're in parallel or anti-parallel. Yeah? And that's what measured here. So the measurement curve here shows directly that we were successful in injecting electrons into that semiconductor nanowire here, and that we are able to produce spins in the nanowire. It's not not the ideal measurement. It was really quite tricky, and from experimental point of view, the signal is really small here, but it's a starting point to get electrons into the nanowire. Okay, I think my time is over, so I would like to thank all the people involved in that study here. So these are the people involved in the quantum transport. You see there's even some Spanish guy here. He came actually from Erasmus to Aachen and stayed in our group and did his PhD. And he's staying in Germany and is married now to some German women. So we have some Spanish contribution here. We also have from theory, we have the support of Andreas Bringer from the neighboring institute and from Marco Palla from Minatec in Grenoble. And these are the people for the growth of the nanowires. Okay, so with that conclusion, I would like to thank you for your attention, and if you have questions, of course, you're very welcome. Thank you.
Thank you very much. Is there any question or comment? Yes.
Yeah. So, in the case of these conductance fluctuations in the presence of magnetic field, so you say that the potential has radial symmetry.
Yeah.
But then you always plot the nanowires not showing circular symmetry, right? With some hexagonal or something.
Okay.
Is that?
That's right. One thing is, if you talk about the conductance fluctuations, all the theory is more or less for cut-off two-dimensional systems. Yeah? If you look, because it's a quite old phenomena, mostly people study two-dimensional systems where you define a wire by simply lithography or whatever. Yeah? So that's the theory we use, because there isn't any better theory for these radial nanowires. On the other side, if you look on our nanowires, of course they aren't radial symmetric. You have a hexagonal symmetry, but that's more difficult to calculate. Yeah? So the simulations we did we did for the nanowires. If we looked on the Rashba effect, or if we looked on these Korshner nanowires, were all done for circular systems. So just because we are not able right now to do a more detailed geometry into the potential. Yeah? That's more because we're not that far yet. Yeah. I think because radial symmetry is relatively easy to calculate, you can quantize everything in angular momentums and so on. If you have a hexagonal shape, it's more tricky. But people did that. Some people worked on that, and but it's more work.
Would you expect some signature on the shape, whether it is an hexagon or a pentagon or
yes.
on the conductance?
One thing you can you expect is if you have, for instance, these Forschungszentrum nanowires, you have this hexagon, you expect that right at the corners you have some potential well. So you have some electron accumulation there. I think there was some Italian group, you see as well? Some people from Italy, they did a more detailed calculation, and they took this into account, and what they end up at the end was that you can simply assume some quantum well at the corners of the hexagon. And then of course you have some periodic boundary conditions, and some kind of periodic lattice with periodic boundary, and then you can start to calculate everything. What you get at the end is, if you look at the potential, what this all ends up, if you do a more detailed calculation, is that you what it all ends up is that you get some gap here. So as soon as you have some scattering centers introduced, or if you have some substructure, then you have some gaps here. That's what you expect.
Maybe it was Goldoni's group in
I think they were. Yeah.
Maybe another question for the last part.
Yeah.
You mentioned that this transistor effect has been realized in practice.
Yeah.
In your lab? Or?
No. It was in, you know better, right? It was in Korea.
Did you mean this Korea?
It was this Korean experiment.
Yeah.
It has not been reproduced very much, I think.
No, I think it was the only report I know about, and I think you also did some calculation that it's right at the edge. I think the transistor, the electrodes have to be quite close to each other. If they are too far apart, then you have too many precessions, and everything is scrambled because of scattering and so on.
In the multi-channel regime, we saw that. The operation of the spin transistor was not very robust. So there were some random oscillations due to multi-channel, to channel interference.
I mean, we have some doubts on the experiment. That's why I asked you.
So I'm lucky we didn't do that experiment. No, what I mean, the structure we have here. This can be. This can be in principle also a spin transistor, but we haven't. Actually, this structure died in the meantime. That's why we couldn't continue the measurement. What we also wanted to do is to do the Hartley effect. So if you apply perpendicular magnetic field to the spin precession, I think that's good proof also that you injected spins. But this could be in principle, of course, also a spin transistor at the end. We haven't done that yet.
Can you gauge this structure?
Yes, we can. Not here, to be honest. Here, in order to get a good spin injection, we had indium nitride, which was even doped. So it's almost metallic. So here, the gate control is really lousy. But in principle, one can do that from using a back gate.
The periodic oscillation of the conductor can be used for something, or the application that is based on this periodicity?
I mean, you can always think of a transistor, but it's more, first of all, it's fundamental study. So we are thinking if this switching is maybe, if one thinks of electron interference for switching purpose, you need to have some mechanism where you don't have to change that much charge, but the switching due to interference is faster. So we're thinking of maybe using that, but we're not that far that we can present a device out of this. So this is more, what we are interested in is this transition. I mean, usually you have out of Bohm effect, you think of trajectories, that the electrons are walking in path. And here we now shrink everything that far that we have one coherent state. And so we have a quantized state. And in that picture, how does the transport behave? Yeah? And the next step is what we discussed this morning already, that one can do quantum dot measurements as well. Yeah? So if you put some gates on top, and then you can confine the nanowire so that you have a quantum dot, which has also a circular symmetry. Yeah? I think Klaus Enzi did these experiments on planar structures, where you had a Van Bohm ring which was that small that it was a quantum dot at the same time. Yeah? And, so we can do similar things, but the nice thing here is that the structures can be made really small, yeah? Because you can go to much smaller structures than you can do by lithography, because this is grown here. Yeah.
So I have a question with respect to the last part of your talk.
Yeah.
In the last part.
This one.
With the ferromagnetic conductance.
Ah, okay.
So in that case, it's supposed that you can, in that way, have some spin bias injection.
Yeah.
Yeah. So then you can also form. I mean, one can even form a quantum dot and do some spin transport with some spin bias there.
Yeah, so the idea is that you have, I mean, the problem is that the measurement we did here was a non-local measurement. Yeah, because if you do a local measurement, if the current is simply going from here to here, you get something like the GMR effect and so on, but you get a lot of side effects as well. Yeah, so that's the reason. The mechanism here is that you inject the current from here into the nanowires. The current is flowing like this, but at the same time, the spins are diffusing also in that direction here. Yeah, that's the mechanism, and I mean that's what's I didn't show this in detail, but you have an imbalance of electrons of different spin directions. So if you inject on this electrode here, yeah. You have electrochemical potential for spin up, which is higher than the electrochemical potential for spin down. And then if you go now along the nanowire here, along to the left, then the electrochemical potential is decreasing here, so it's going to the equilibrium level, but you still keep the imbalance. Yeah, that's the mechanism here. So I don't know if, probably if you would have a barrier here, so you can use that, definitely. Yeah. And so by the second contact, you're picking up the electrochemical potential depending on the orientation of the second contact. So this is the safest method to clarify if there's really some spin injection here. Yeah, you always should do a non-local measurement. If you do a local measurement, you have everything like Hall effect or whatever. Yeah, it's really messes up everything. Yeah. But it's really tricky, this measurement.
Maybe we can stop here. Thomas is staying today and tomorrow morning in room 205. If anyone of you is interested in discussing further. Thank you very much. Yeah, I was concerned about the students.
Ah, okay. Yeah, I saw that you were getting nervous.
No. And isotopes, I have also a question. You talked about this weak anti-localization as a way to see spin orbit effects.
Yeah.
And isotropies with magnetic field. You have the wire and then you move the magnetic field in different direction. I think the spin orbit, depends on the type.
But we haven't studied this, but might be interesting. Yeah, so I think
spin orbit should give some different properties, whether magnetic field.
Yeah, maybe it makes a difference. Yeah.
Conductance.
Yeah. Yeah.
Okay.
Yeah.
So
Yeah, also Andre asked me if you apply perpendicular magnetic field to these core shell nanowires, what happens to them if we...
Right.
Yeah, I mean, this along the nanowire thing was trivial because you get these
gauge is very nice. Yeah, actually we've been discussing.
But the other one is more complex because then you have these. I think then you get these lambda levels and so on, and it's quite tricky system. And
right, I think you get the coupling between different channels, so it's not so simple. But at least numerically.